We can slowly start. So it's a pleasure to have Chiara here. We actually have never met, but we come from the same place. So I think we were born very close to each other. So Chiara studied at Politecnico, I guess. I studied at the university, but we were in the same town, and we shared some of the professors. And then when I came back from Australia, she moved to do a PhD at Oxford and basically stay there, right, Chiara?
That's true. Yeah.
She worked on foundation, so slightly different from what we do here, or at least from what I do here. But we recently discovered that there are some interests in common about these temporal correlations and what we call temporal entanglement. And so I invited her to give us a talk with the hope that we can kind of start discussing about these things in the future. Okay, Chiara, stage is yours. What do you prefer? Do you prefer that to give the talk and we do the question later, or?
I'm happy with either. If you want to interrupt me as I'm talking, that's completely fine with me. I put together a kind of introductory talk, and I'm very happy with informal settings. So if you prefer interrupting and asking questions, actually that's good. So maybe that helps not losing the audience along the way. So I'm happy with anything.
Everyone then should feel free to unmute, because do not raise hands and things. So let's keep it there.
Yeah, I can't see everyone in the. So if you want to stop me, just say I have a question, and then I'll stop. Basically, we do it like that. Okay.
Perfect.
Yeah, great. Thanks a lot for inviting me, and I'm very happy to have discovered that through your letter to me that there is a potential overlap between the stuff that I've been doing and your research. This is coming from, as Luca said, from a very different direction. So I thought I would give an introduction and put the particular paper that Luca mentioned in the context of the broader set of results that we've been building over the past few years. And the title has the part of the temporal witnesses on non-classicality is the bit that kind of Luca was interested in. Hybrid systems and conservation laws will be connected to it in the talk, and it will be explained in what way I think all of these things fit together, and in what way this is connected with the foundations of quantum theory, which is somehow one of my biggest areas of interest. Okay, so let me start with the general problem. So there is a growing set of motivations for looking into situations where the theory of quantum computation, which is, by the way, my main area of expertise, may break down or may not be fully applicable. And this is brought about by the fact that quantum technologies allow us to probe domains where you have a quantum system, which is a probe, something that can be controlled fully quantum mechanically in a laboratory, a qubit. So this could be degrees of freedom of a photon field, or it could be a particle that can be put in a superposition of different locations, like in an interferometer. Anything that can work like a qubit, spin degree of freedom of an electron or a different particle. And this system then interacts with another system, M, which, on the other hand, may or may not fully obey the laws of quantum theory. And this could be intended at the fundamental level. So M really could actually departure from the laws of quantum theory. In this case, we're thinking of gravity, for example, There are lots of proposals for theories that are semi-classical to incorporate the gravitational field into a fully quantum world. Or it could be, M could be a particle that is mesoscopic, so it has a larger scale than Q. And so it may collapse away from the laws of quantum theory or obey a different dynamics where Schrödinger equation, unitary Schrödinger equation is modified by added terms. And it could also be the case that M is actually, does obey the laws of quantum theory, but it's so complex that the laws are intractable. So that's like less fundamental, but still useful motivation to look into a system where M has dynamical laws that are not fully soluble. And so you're left with this question of how do I look at this hybrid system? How do I describe this system? And of course, there are different approaches to this. You can use approximation schemes of different kinds, weak coupling type settings, open systems, quantum open systems. All sorts of different approaches are useful and have been looked into. You can also look into hybrid quantum classical systems. But I'm more interested in taking a more principle-based approach. So I'd like to commit not so much to formalism of a specific dynamical equation. And I would still be able to describe or make predictions or statements about this system. And particularly, I'm interested in the situation where we would like to test whether this system M does or doesn't have some quantum features. So we are in this scenario where I'm trying to convince some skeptic of the fact that M does ultimately have quantum features. So its dynamics is not fully describable by simply a classical model. And so this is ultimately motivated by this century-old question, which is whether quantum theory is ultimately universal or not. Whether a system where you have a quantum side coupled with a classical side is possible, and under what assumptions this is allowed. And the point of the work I'm going to present is to show that if you stick to some general axioms that seem plausible for a reasonable physical theory, like locality, certain assumptions about how systems should couple with each other, then it's reasonable to expect that if you have one sector of the universe that's quantum, then it is going to be the case that everything else also has to be quantum. So my position on this is that, yes, of course, mathematically it's conceivable to have ways of coupling a classical system with a quantum system. But ultimately, if you want to impose physical principles that resemble reality as we know it, you would have to rule these models out. And ultimately, the quantum theory is universal. So that's a kind of angle from which I'm coming to this problem. So this is just diving into the definition of a hybrid system in the way I think about it, because hybrid systems have been used in the literature in all sorts of ways, and I'm using it in this very loose meaning of having a quantum system that interacts with another system whose dynamics is partly unknown in the way that I said earlier. And here are some examples of what this could be. So the origin of the problem goes back to, obviously, to the early days of quantum theory, and particularly to the early days of quantum gravity, when people were concerned about how to incorporate gravity within the quantum formalism through some sort of quantization. And Bryce DeWitt, who looked into this problem very, very carefully, had this kind of funny way of talking about the totalitarian property of quantum theory, through which he meant to say that quantum theory has the property when you couple it with some other system, it has to spread to this other system as well. So he had an argument saying that to demonstrate the fact that if you quantize a system, then this implies actually the fact that any other system to which this first system is coupled must also be quantized. And this result was proven by him in the context of Lagrangian mechanics, and it was proven with the intention of showing that actually the program of quantizing gravity was worthwhile. Because at the time, like just even now, this is still true, there is still this issue of, do we really have to quantize gravity or not? I mean, after all, general relativity is a classical theory. It describes gravity perfectly as far as we know in terms of experiments, at least at the scale where one can perform experiments. And so why bother with the quantization of gravity itself? So if you look at his argument, there are some aspects that can be improved in the sense that it has a set of very specific assumptions, and specifically is using the Lagrangian formalism, which, if you like, it has lots of axioms built in it. And so one could look into, and that's what I decided to do at some point, to look into how to generalize this argument in a context where you don't need to assume all of those bits of formalism that you do have to assume in the original proof. And the method I used was this work that I developed with David Deutsch here in Oxford during exactly my PhD, which is called the constructor theory of information. And now I don't want to go into the details of this because it's only tangential to what I want to say later, but it's really the origin of the kind of thought process that led me to actually land on the temporal witnesses of classicality, of non-classicality, that we'll talk about in a bit. So the constructor theory of information has lots of aspects to it, but the thing you want to know for this talk is that it's a framework where you can describe quantum systems as a special case of another class of system which we call super information media, which are constrained by a set of axioms, and they are a subset of systems that we call information media, which correspond to any kind of physical system that can embody something like a classical bit of information. So super information media are a strict subset of information media, and they have additional properties. And in fact, they have all the qualitative features that make quantum systems able to perform quantum computations. So things like irreducible perturbation caused by measurement and superposition principle and so on, they are shared by all of the super information media. But the key point about all of this is that you can describe both super information media and information media and quantum systems as a special case of the latter in the same framework, where you don't have to specify a dynamical law, but only constraints on what transformations are allowed or not allowed. And this is very useful because for the problem I just said, because in the context of hybrid systems, if you don't want to really use a dynamical approach to the problem, it's useful to have axioms that are formulated in this general framework to treat these quantumness and non-quantumness on an equal footing. So that's what the constructor theory of information is useful for in this context. And once you're in that framework, you can talk about a particular property, which is the thing that we are interested in or will be concerned with for the whole of the talk, which is the concept of non-classicality. So when you think of classicality, or in fact, when you think of quantumness, people mean different things. So you can think of violating Bell inequalities, for example, or you can think of showing some sign of quantum coherence, whatever that may be defined, however that may be defined. And here I'm looking at a very minimalistic version of all of these properties, which is not as strong as, for example, Bell non-locality. It's not as strong as quantum coherence, but it's enough to say that if a system is non-classical in this sense, cannot be described by a classical model. So non-classicality is the property of having at least two variables, I call them X and Z, that are incompatible, and this is a generalization of the notion of non-commuting in quantum theory, but it's characterized in a way that doesn't use commutators. So it's to do with the fact that you cannot perform a perfect copy of all the values of x and z simultaneously. Obviously, this reminds you of the Heisenberg uncertainty principle, if you like. So it really generalizes the idea of incompatibility in the context of quantum theory in this more general framework where we are not using the dynamics of quantum theory. And it's based on the fact that it is impossible to perform a certain interaction that would result in the copy of all the values of x and all the values of z simultaneously. And this is a good characterization from the information-theoretic point of view, and it generalizes the idea of non-commutativity. So if you want, in your mind, you can think non-classicality is the same as having non-commuting variables in your system, but it's defined in a more general way, so you don't need to commit to the commutator formalism to define it. And that's the whole point of this generalization. So once you have this notion, you can then prove and this is something I've worked with Vlatko Vedrol, who's a physicist here at Oxford, who actually was interested in the Witt's argument as well. And somehow we started discussing about whether it made any sense. And then we decided that perhaps we could make it a bit stronger. And so you can argue for the same thing that the Witt wanted to argue for, but now you can say it in a more general way. So you can have some axioms that are formalism or dynamics independent. So one axiom is locality in the sense of no action at a distance. So when I say locality, I could mean many things, and I mean this. I mean really the fact that there is no action at a distance. So if you have an interaction that affects a subsystem in your in a system that's made of many subsystems, this interaction should not affect instantaneously other subsystems. That's all this means. And then you have a second axiom, which is called the interoperability of information, and I'm happy to talk about it maybe in the remaining time after my talk ends. This is an assumption that constrains the way in which Q and S can couple to each other. And it says that, so if you have a system that that has a certain number of distinguishable states, so it can contain information and it has a certain size as far as how many distinguishable states it can hold. And you have another system that also has the same property, so it can contain information. If you put them together and you consider the composite system, there is a certain rule of additivity for the total number of distinguishable states that you have overall. These properties are assumed routinely for bits. So if you have one bit and another bit and you put them together, no matter how they are embodied physically, you expect to have 2 bits worth of information. But if you think about it, it actually requires a certain constraint on the algebraic properties of the set of operations that you can perform at the global level once you consider the operations that you can perform at the local level. So that's a kind of constraint in the sense of how interactions compose with each other when you consider composite systems. And then there is an assumption about the fact that the dynamics, whatever it is, has to have a one-to-one feature. So it should map different points into different points. So these are the 3 assumptions, and under which you can prove a generalization of the Witt's theorems, which says that if it's possible to couple a system Q with another system S, and Q is a super information medium, so it's got this non-classicality feature, then this other system S also must have the non-classicality features. So this is like about the totalitarian property of non-classicality, if you like. And it's the generalization of the Witt's argument. Now, from this, to get into the witness, there's an extra logical step. Does anybody have any questions so far of any kind, even at the very basic level? I hope this is reasonable so far, what I've been saying.
So, can I ask you something?
Yes.
So this non-classicality, so it's obvious to me that if you have some kind of how do you say, non-compatible quantity in Q, then it's clear that if you look at them as Q tensor S or whatever how you want to call them, they are still there, right? But are you saying that there should also be this non-compatible value directly in S without?
Yes.
Okay.
Yes. Yes. So the point is, that's a very nice way to put that. Exactly. So it's not just when, so this is the old age problem of having a quantum system and then being looked at by another system. I called it S here. I think I called it M in the previous slides, but it doesn't matter. You're always wondering, is it okay that a classical system or a classical observer, M, a macroscopic system, looking at a quantum system, is it a kind of is it a situation that's acceptable? And what this says is that fundamentally, even though maybe you can have some approximate model where this is acceptable, if you want to hold on to these axioms that I just wrote here, of course, it may be that you don't like those axioms, in which case the result is not true. But if you stick to those axioms, which seem sort of reasonable for a number of models that we already know about reality, then it's not just the case that Q has these incompatible variables, but they somehow spread to S as well. So S must also have these observable variables that have this incompatibility property. And basically the proof works by contradiction. So in a way that you assume that S doesn't have them, then you couple it with Q under the axioms, and then you show that this violates one of the axioms. In fact, a number of them go wrong, but locality is a very strong one, and I think that's the one that there are some interesting models that are non-local and violate this theorem, obviously because they don't satisfy the axiom. But it's an interesting trade-off somehow that it tells you that you really have to compromise on some important property of reality, such as locality, in order to stick to this classicality on S. Otherwise, if Q has incompatible variables, S must have them as well. So this forces the quantization of other systems, at least at the theoretical level. Then, of course, the question of whether you can observe these things, it's a different question. But that's what this says.
Okay, thanks.
Cool. By the way, this could be measured, and this may be into some area that is of interest to you and you guys more generally in the audience, that I'm not assuming any particular measure for this incompatibility. The incompatibility simply says I've got these two variables and I cannot perform a certain transformation on them, which requires them to be copied perfectly. That's what I mean by being incompatible. But to what degree they are incompatible, which of course you can talk about that in quantum theory, because you can put some measures of incompatibility with commutators and using the norm of operators or a number of other possible measures. You don't have to assume them here. However, you could use that and maybe use some generalization of entropies used in a judicial way in this context. And that would be very interesting to look into, because this is just a qualitative, not a quantitative result. It says if you have a little bit of incompatibility on Q, it's got to be there on S as well in some form, a non-zero incompatibility. But how much, that's the theorem doesn't specify. Okay, so then from here, so I'm just checking the time. From here on, the shift will be slightly, the logical shift, so the sort of focus will be on a slightly different problem, which is kind of related to what I just said. So now we have this argument, and the next question is, okay, you're telling me that M has to have non-compatible variables, but can one actually test that this is the case? So this is what leads you to this idea of witnesses of non-classicality. And the word witness was used a lot within quantum information theory. Here is used in a looser way in the context of this domain where quantum theory's laws may not apply. And so I talk about it in terms of a protocol that you can implement in principle, a thought experiment that you can implement in the laboratory, where you have a quantum probe, a quantum system Q that now can be operated on in the lab. So it can be measured on, so you can measure any observables on Q. It's a fully fledged quantum system interacting with this mystery system M, which I called S in the previous slides. And the goal of this witness is that you want to measure some properties of Q and then use some theoretical argument, which hopefully rests on these minimal assumptions, to infer that M must have, excuse me, these non-classical features. So the goal is to prove that M is non-classical. It has these incompatible variables by looking at Q only. So I don't know, for instance, you know, M is a macroscopic system that can interact with light. There are some photosynthetic system in the bio world, for instance, and Q is a photon field that has quantum features, and you're using it as a probe to see what M does when it interacts with Q. But you don't measure M directly, you just measure properties of Q. Okay, so the first witness we came about, so we realized we could implement is based on this general witness theorem, and it's in space. And the reason why I'm emphasizing the space aspect of this is simply that we will then try to generalize it in time, and this will land on the work that Luca mentioned earlier. So the idea here is that you use two probes, not one, two. There is a reason for that, and I'm happy to talk about it in the questions. So you use two probes, and the idea is that if you can interact locally with the system M, with Q and Q primed separately. So Q and Q primed are not talking to each other, but there is an interaction between Q and M and Q primed. And if you start with Q and Q prime being, for example, in a product state, so they are uncorrelated, and then you wait for a while, and you're sure that nothing else is actually getting in the way, it's only M causing this interaction to occur, and you end up with Q and Q prime entangled to some degree, then M must be non-classical. This is a generalization of the, for those who are familiar with the quantum information language, with the local operation and classical communication theorems, which say that if you have a fully quantum, multipartite system in quantum theory, you cannot generate entanglement with local operations and classical communications only. But those theorems don't apply here because we can't assume quantum theory to hold for M. We are in a scenario where M may not obey quantum theory, so we need to use these more general axioms. And so this is, if you like, a generalization of that theorem to this general context. And so the two assumptions that I'm using again are locality, which is almost, I would say it's necessary even to talk about just local interactions between Q and M and Q prime and M. Otherwise, it wouldn't make sense to even think about it this way. And then interoperability of information, which again allows you to think of interactions occurring between these subsystems under some reasonable assumptions. And so these are the two axioms, and the theorem is proven after, with the same technique as I mentioned earlier. So this is a spatial witness because we are talking about spatial correlations, if you like. The entanglement is created between two space-like separated objects. So Vlatko and I landed on this theorem because we were thinking of generalizing the Witt's theorem, but actually in the end we realized that this is very useful, and this is an aside, for testing quantum gravity in the laboratory. So this is like a branch of my work at the moment. And so we actually proposed a thought experiment where you can use M, you can think of it as gravity, and Q prime, there are two quantum masses. And you want to check whether gravity is quantum or not. So we know that there is a controversy about this, and no one has been able to test any quantum effects because usually they are thought to be very difficult to test in a laboratory, given that they require huge energies to be present. But what we found out in this particular proposed experiment is that the masses you need to generate entanglement through a gravitational field are not as big as usually people thought. So they're not Planck's masses. They are several orders of magnitude below. So they're about a nanogram for those who are interested in these kind of things. And this was also corroborated by a proposal that was put forward by Sugato Bose and his team at the same time as ours. So somehow we discovered that we had a similar proposal that was based on somehow different rationales, but ultimately we kind of converged on the proposal and on the sort of numbers. And now people are actually looking to implement this experiment, which is nice because it's a low energy test of quantum gravity, if you like. So that's a sort of small application of this witness. But reason why I'm interested in this, other than this experiment, which I find very exciting, is really the theoretical side of it. I think of it as a sort of generalization of Bell's theorem in a context where you're not assuming you have this extra complexity of trying to prove that something is quantum, which may not obey quantum theory's laws, and they cannot be directly measured or probed. So, Bell's theorem can be applied to number of, to certain statistics that you get out of multipartite systems, bipartite system. But somehow you have to be able to access the statistics directly, so you have to measure these systems one way or another. Whereas here, M is not measured directly, so there's one step removed from how Bell's theorem works. So that's how I like to think of this result. And this is where the temporal entanglement thought came in, because at this point you can think of, well, you have a spatial witness of non-classicality. Is it possible to think of a temporal version of it? And this is something I started thinking about, prompted by my student Giuseppe Di Pietra, who actually is the person who has been the driving force behind all of this. He's currently doing a DPhil here in Oxford, and he came up with this. We found this question very interesting together, and then he sort of thought of various ways in which you can actually generalize this spatial witness theorem into the temporal version. And here I'm going to give you just a few logical steps, and that's going to be the end of my talk in a few slides. So again, the same logic. So ideally you would like to start with minimal assumptions, but initially with Giuseppe, we decided to work within the formalism of quantum theory. So what I'm going to say now is not as general as what I just said so far, because we are using the formalism of quantum theory to describe Q primed, and Q and M. And so it can be generalized, and that's what we're working on at the moment, but we haven't got there yet. So that's just a word of caution that somehow this shows more like a thought process of leading to this generality that we had in the spatial witness theorem, but this is not as general as that. Still, I think it's of interest, and maybe it overlaps nicely with some of the things you've been doing. So the idea now is to have one system Q, so not two is one, and it's evolving in time. And it's again the quantum probe, so it can be measured and addressed, in theory, in principle, in any possible way you like. And now M is not mediating interactions in space, but it's inducing a dynamical evolution on Q. So it's more or less mediating an interaction in time between Q at time 0 and Q at time 1. And the first version of the theorem we tried, this is some work we did during Giuseppe's master's actually, is that if Q can evolve from one state rho at T0, these are quantum states now, to a different state, rho t1, and this rho doesn't commute with rho t0. And you know that the evolution has been induced by a unitary Hamiltonian that couples Q and M, but not other systems. Then M must be non-classical, assuming, and that's one of the axioms that replaces locality, assuming that there is a conserved quantity, an additive conserved quantity on Q and M jointly. So here is an interesting thing that Giuseppe and I found out, which is that maybe not so surprising, but interesting, that instead of having locality, if you look at these temporal witnesses, a sufficient condition for a theorem to be proven of say similar flavor is to impose a conservation law of some additive joint variable. And that was interesting. So then we thought of using this result in some context. And this was a contribution of Vlatko. So Vlatko has a huge interest in quantum biology, and he's always been keen of finding ways of proving that biological systems are in fact have some quantum features. And so we tried to apply this this witness to just checking the time, yeah, to a quantum biological system. And so a very simple toy model, I would say. So this is not really, doesn't have the, doesn't want to be a specific experiment being proposed, but it's a kind of maybe motivational toy model that you can think about. Is a situation where Q is a single photon probe, and M is an exciton that lives on an N 1D biopolymer. And so the idea is to use the probe Q in order to test that this exciton and therefore the polymer have some non-classicality in them while interacting with each other. Obviously, we know that excitons are quantum, but the point of this thing would be to show that in a certain specific experimental setting, there is some quantum effect or non-trivial, non-classical effect on the exciton when n is large. So that's the reason why this would be interesting for quantum biology somehow. So we have a model where we are thinking of the single photon probe acting on creating the exciton on one side, and then you wait until time goes from T0 to T1 and the exciton relaxes along the chain. So it spreads out and then it recombines, and this emits another photon or another photon field, depending on what kind of application you're thinking about. And basically this photon probe is now in the state rho T1. And now if you can show that rho T1 is now delocalized as opposed to the original rho T0, which was sharply localized on site 1, this is your witness of the fact that you allowed for a coherent evolution of rho T0 to rho T1. And indirectly, this allows you to show that M must have had these non-classical features in it. So this is an example of an application. Of course, it's a toy model, but to us sounded fun to think of it, even just to think practically about how this would pan out in a specific context that doesn't involve gravity, because gravity is very exotic and kind of difficult to relate to sometimes, especially if you think of experiments that you can perform right now. Okay, and finally, we have this second version of the temporal witness of non-classicality, which is not quite as general as the theorem we have initially, but is the thing that uses entanglement in time. Again, this was an interesting collaboration between myself, Giuseppe was the driver of all this, Vlatko, and a bunch of experimentalists led by Jonathan Jones, who is an NMR experimentalist who works here in Oxford. Okay, the theoretical part is a variant of what I just showed you now. Again, there's only one system Q, and Q evolves from some state at T0 to another state at T1. And M is the mediator of this interaction. And the theorem says that if you're able to generate what in the literature is called entanglement in time on Q through a global interaction that conserves this additive quantity, we call it energy here, but really could be more general, then M must be non-classical. And in our work, we looked at entanglement in time as measured by achieving a violation of a generalized temporal bell inequality, which is the CHSH inequality on Q. So specifically, this is a bit more, this is kind of somehow part of the paper. So we looked at this quantity, which is usually bounded by 2 in the classical case. And now it's calculated in a slightly different way from the standard temporal bell inequalities type scenarios, because we have M included in the scenario. So you perform certain measurements on the probe Q, then you let M and Q interact through some general unitary that only has this constraint of conserving a certain quantity on M and Q. And then you measure other observables again on Q, and then you compute this correlator. And if this exceeds the bound, then this is not just a way to check that Q is capable of showing entanglement in time, but it's an indirect witness of an M's non-classicality. And then in the paper, we have a nice NMR simulation with a very simple circuit where M and Q in the NMR simulation, you always need, so you can't do projective measurements, so you always need an ancilla for that. This is the reason for this A here, implementing measurements of the relevant observables. Here only 2 are showed, but you can measure a number of them. So this was a particular circuit for the simulation, and there was some interesting data with the full line being the theoretical prediction and the dotted line being the experiment. So the red lines are about the classical mediator M, and the blue lines are the non-classical mediator. So this was an experimental demonstration of these ideas. Okay, so that's the paper, and now we're looking for ultimately doing the final generalization bit, which is to actually, as we already said, it's nice to have this parallel between the key axiom in the space case is locality, and the key axiom in time is the conservation of a joint observable Q and M, for example, energy. And now what we want to do is to use constructor theory's formalism to make this latest version of the witness as general as we have it in the spatial case. And so let me just say some open problems other than this specific one that I mentioned. So in addition to this, exploring further connections with the theorem of entanglement in time, which may be something that relates to your work, there is this interesting idea that conservation laws are connected to this concept that's often referred to in the literature, which is called locality in time, which has different definitions, and perhaps this would be a different angle on it provided by this type of witnesses. Then, of course, what I've just said so far is not relativistic at all. So we're always thinking of something local in space and time, as we do in quantum information theory more generally. But it would be interesting, specifically because of the application to gravity, to imagine a situation where these results become covariant in some way. So you are thinking of generalizing this formalism that's general enough to hold quantum and classical features, also to the case where you have relativistic transformations at play. This is the most non-trivial thing to do out of all the ones I've listed here. So it's the one that is just at the moment as a sort of thought, but it would be nice to do that. And then obviously we have some collaborators who are interested in implementing some of these witnesses, either as a simulation like what we've done so far, but what would be really cool is to actually do an experiment, maybe applying it to other than gravity, which is suddenly, you know, 10-year type horizon experiment is very difficult to perform still. Something to do with maybe quantum biology, maybe some of these quantum biopolymers, thinking of some hybrid systems that can perform some hybrid quantum computation. And that's something we're also trying to develop. I think my talk is done, and you know, thanks for listening, and I'm very happy to get questions or discuss more. And feel free to get in touch with Giuseppe as well, who is, as I said, he's you know the person who's been driving all of these results, and he is very interested in this application to the temporal witness side. So yeah, thanks for your attention. I'm happy to have any questions and discuss more.
Okay, thank you very much. Okay, so questions. I obviously have a few of them, but let's see if someone else want to start. Please feel free to directly unmute if you want to ask something.
Yeah, that's
okay. Then maybe I start. So can you go back to the slide in which you had the actual NMR circuit?
yes. Can we share it again?
I wanted to and also where you kind of define this one. Yes, indeed.
Yeah, let me just put it. Yeah.
So just to understand, so you say EAB would be the trace of trace is the total trace over both M and Q, right?
Yes. So this is a notation that uses. So these are full support operators on all the. So they are not. This is not a local operator on Q only. So you can think of it as a tensor or identity tensor A for Q. So these are. This A is, if you think of these two as qubits, is a 4x4 matrix. So it occupies simply a notation that uses a product of operators rather than the tensor product. If you wanted to write it in tensor products, you would have to represent A as identity tensor A,
Okay.
which is now operating only on Q. But that's the notation. A B is the same on Q, and rho M is now the state of the system M. So it's the local density operator for M, and we're thinking initially rho and M and Q are they are in a product state for simplicity.
Okay. And how can I? So is it easy? Maybe I don't see it directly, but you're saying that just measuring these ancilla qubit in the NMR gives you this expectation value.
Yeah. So this is a unitary way of representing a measurement of. This is a control knot, but it's effectively a way to measure the sigma z operator on Q.
Mm-hmm.
And then you read out the result of the measurement on A, and this jointly with so this is a Hadamard gate, which is a rotation from Z to X. And so if you consider this thing here, this is effectively a measurement of sigma X. Here it's only a pair of variables, but you would have to measure all the four possibilities of ZZ, ZX, XZ, and etc. So here is just a figure from the paper where you represent one measurement,
I see.
one possible combination.
I see. Okay,
and this is a feature of the NMR simulation. So if you want more details of the NMR actual implementation, so if you're interested, I'm not an expert about NMR at all, so I think I understand it at this theoretical level, but the details of how that was done, they are beyond my understanding. So
okay, no, I think I more or less see it. Okay, thanks. Can I ask? Sure. Let me mute. So I'm.
yeah.
Yeah, I have a question about this. Well, the non-classical mediator, that it seems that only breaks the bound for a small amount of time. Do you have any idea why that this happens? And also, if you were to look like at long times, would you be able to see some kind of breakdown of this bound at some point, or is it for all the systems that you think it's something like that, a bump and that's it?
Yeah, this is a nice question. I think there was a sort of sweet spot for showing this violation, and somehow we went with this was in the theoretical simulations you could do various you could play with various aspects, and then it was easier to show for a longer time. So there were lots of possibilities. But I think somehow with the experiment, I think they had to look into various trade-offs also to do with the noise. I think you can see that some points are quite far from the theory prediction. So in that sense, I think there isn't a fundamental reason for that. It's simply that this was the optimal thing to showcase the results, and it worked out like that. If you want a more specific reply, maybe you can ask the experimentalists, because they might have a more reasonable explanation for why this is the case. In terms of the theoretical results, this is so the way we're looking at this is really to use a unitary transformation. So somehow we don't expect a damping of this by waiting for longer times. Because it's basically a periodic, if you like, type of interaction. And so I think this should be, so there's no approximation as far as the, so initially I think we solved the thing for small t, but then we realized actually it was okay to solve it exactly, and Giuseppe actually managed to do that nicely. And being a simple system of, we did some toy models with 2 qubits where m is effectively a qubit, but you're restricting its degrees of freedom to just be one variable being involved in the interaction, and then you gradually introduce more bits of the non-commuting variables, and that shows the transition from a classical, fully classical M to a non-classical M. And I think this can be done exactly. So in that sense, there shouldn't be a bound, like a constraint on the times, short times. I mean, it's a nice question. Hopefully this is robust in that sense.
Mm-hmm. Okay, thank you.
Thanks.
Okay, any other questions? I have a question about the conservation law, right?
Yes.
Because in all these systems, you can expect that there should be some dissipation, and so even though you can model it as a kind of completely closed system, you might expect some lose of or indeed some loss of energy during your things. How does this affect? So you're saying that in case in which you have such a loss, you cannot certify that the system need to be quantum, or is there a degree at which you can still certify? Since here you have a quantitative things like, so can you still?
I like the question.
Yeah.
Yeah. That's a very nice idea that you could somehow. So let me start from the fact that the assumption is I regard it as quite strong, and that's somehow why we also want to make it a bit more general. In that, as you said, it requires somehow an ideal case where your system is not lossy as far as that degree of freedom is concerned. And I think so. We think there's some way. So there are some works by other people that are closely related to my group and Vlatko's group. Particularly, there is this person called Tianfen Feng who is who works in I think Hong Kong, where so he looked into a situation where you actually only assume the conservation of energy to be true on average, so not this exact version, but somehow you relax the constraint and you only require the expected value of the total quantity to be conserved. And in that case, a variant of this result is still true, though maybe it's not as strong as this result. So I'm not so sure about that direction of generalizing this, but it's possible to do that. And now you're asking whether you could actually make a trade-off like a sort of quantitative version of, okay, we violate the constraint a little bit, and then we can still certify non-classicality up to a point. And I think this should be true, because if you imagine to model this as at a higher level with still a unitary, just by adding another system that's representing the losses, it seems to me you're right that a quantitative argument of this kind could be made, and it's a very nice idea actually. That could be a different way of generalizing the result and making it more robust. One way in which Giuseppe was trying to make this more general was that we have a similar in his thesis. I think there's a result where the conservation law is still exact, but instead of having a unitary evolution, you have a CPTP map, but it still has to satisfy the conservation exactly somehow. So it's a lossy thing, but not as far as the conserved quantity is concerned, which is the most difficult thing to certify in an experiment, right? Because you have to sort of make sure exactly that your system is not lossy in that regard, and that could be difficult. So yeah, I think it's a nice idea. I don't know how to do it, but it seems to me it's possible, and maybe that could connect to what you guys are doing.
Yeah, exactly. In alternative, one could think of other conservation law like particle numbers or things like that
Yeah.
are easier to track experimentally, for example.
Yes, it doesn't have to be energy. This is so long as it's additive, in the sense that if you like, if you call, I don't know, AM and AQ, the two variables on M and the two observables on M and Q, you would like the sum of these two operators to, when you consider them as operators with full support, to be conserved at the global level. So I think somehow we only looked into these kind of joint observables, which I think, yeah, number, energy, momentum, all of these things are sort of, they obey these things, especially at low energies.